affective and cognitive disorders don't just light up one spot in the brain. They ripple across distributed, time-varying network dynamics that shift across regions, channels, and time. When we try to model this with EEG or stereo EEG, we run into a massive bottleneck. Most current AI models treat brain signals as either unstructured sequences or rigid anatomical grids. They rely on fixed priors, struggle when channels go missing, and often learn superficial shortcuts instead of true neural representations. Today, we're breaking down RECTOR, a new end-to-end self-supervised framework that fundamentally changes how we model region, channel, and temporal dynamics in neural signals. It's not just another transformer for EEG. It's a structured, topology-aware approach that evolves static anatomical definitions into adaptive functional regions, and it's setting new state-of-the-art benchmarks across both non-invasive and invasive brain recording. Let's talk about why standard self-supervised learning falls short here. The predominant approach in neural signal processing is masked modeling, where you randomly hide parts of the input and ask the model to reconstruct them. On image or text data, that works beautifully. But on EEG and sEEG, random masking creates a trivial pretext task. The model learns to predict neighboring time steps or nearby electrodes using local spatial temporal shortcuts, rather than capturing the global, distributed functional connectivity that actually defines cognitive and affective states. Furthermore, most architectures either ignore the brain's hierarchical structure entirely or bake in a rigid, population-level anatomical atlas. That rigidity destroys robustness. If a sensor fails, or if you switch to a different electrode montage, the model collapses. We need a framework that respects the brain's adaptive functional topology, while remaining flexible to hardware variations. RECTOR solves this with a hierarchical block-sparse self-attention mechanism called RECTOR-SA, driven by a component called Adaptive Functional Partitioning, or AFP. Instead of treating every electrode as an independent token in a flat sequence, AFP dynamically groups channels into latent functional regions. It starts with a standard anatomical prior, like the 1020 system for scalp EEG or established depth electrode maps for sEEG, but it doesn't stop there. During training, a learnable projection head continuously refines this assignment matrix, evolving the partition from a static anatomical scaffold into a data-driven functional topology. This evolution is controlled by an annealing schedule that gradually relaxes the anatomical constraint, allowing the model to discover task-specific groupings that better reflect actual neural coupling. Once those functional regions are established, RECTOR-SA factorizes the dense attention computation into 3 parallel topology-aware blocks. First, topological attention handles the cross-attention between channel tokens and their assigned region tokens at each time slice, using a Kronecker product mask to ensure each channel only attends to its corresponding region. Second, local functional attention models fine-grained interactions within each region over time, using a block diagonal mask and dynamic top-P gating to prune spurious connections based on attention logits. Third, global functional attention captures high-level coordination between regions. This hierarchical design means we never compute quadratic attention over every single channel time token. Instead, we get block-sparse computation that's dramatically more efficient, while explicitly disentangling region-common dynamics from channel-specific high-fidelity signals. Architecture alone isn't enough. You need a training objective that actually forces the model to learn meaningful neural representations. RECTOR introduces masked topology and representation learning, or MTRL, which unifies 3 complementary self-supervised objectives into a single forward pass, backed by an exponential moving average target encoder for stability. The first is masked predictive modeling, or MPM. Standard reconstruction only minimizes signal-level error, which often leads to representational collapse. MPM couples input reconstruction with latent representation alignment. The model predicts both the masked raw signals and the masked latent features. The reconstruction term anchors the encoder to the actual electrophysiology, while the alignment term uses a stop gradient on the target representations to force the latent space to retain semantic information about the masked context. Together, they ensure the model learns features that are both grounded in signal detail and predictive for downstream tasks. The second objective is topological structure modeling, or TSM. This is where RECTOR explicitly regularizes the learned topology. Since the channel-to-region assignment is discrete, the model uses a straight-through Gumbel softmax estimator for end-to-end differentiability. The network is tasked with predicting the assignment matrix in the latent space, supervised by a stable target encoder, while simultaneously aligning those predictions with the input space assignments via row-wise cross-entropy. This compels the latent representations to be structurally faithful to the functional topology, preventing the model from learning trivial or decoupled embeddings. The third is cross-view consistency, or CVC. During pre-training, RECTOR generates multiple disjoint masked views of the same trial, sampling from different structural domains like region, channel, time, and their combinations. CVC enforces that the global semantic representation remains invariant across these diverse intrasample views. By minimizing the distance between pooled representations from different masks, the model learns robust, topology-aware embeddings that generalize far beyond the specific masking pattern used during training. The result of this unified approach is a model that consistently outperforms leading task-specific and foundation model baselines across multiple benchmarks. On EEG emotion recognition datasets like sEEG, CDIV, and DEAP. RECTOR sets new state-of-the-art results in both subject-dependent and subject-independent settings. On invasive sEEG task engagement classification with the MSIT and ECR datasets, it similarly dominates. But the real story isn't just peak accuracy. It's robustness. When we simulate real-world sensor failure with random channel dropout up to 50%, RECTOR's performance decays significantly slower than baselines. It effectively reconstructs missing local features from the global context. We also tested cross-montage generalization, transferring representations between completely different electrode layouts. While fixed topology models crash, RECTOR's adaptive partitions minimize this decay, proving that the learned topology is structurally invariant to physical hardware shifts. And because of the block-sparse attention, it achieves all this with lower computational overhead than full spatiotemporal transformers. For clinical AI, interpretability isn't optional. We need to know the model is looking at the right neural circuits. AFP consistently learns spatially coherent refinements beyond the initial anatomical prior. It merges nearby channels that were previously separated, splits broad anatomical regions into finer substructures, and repeatedly forms anterior subgroups and lateral chains that align with known functional networks. When we visualize the attention matrices, we see a clear block-diagonal structure, with the strongest activations concentrated in region-level tokens rather than noisy channel-level connections. Class activation maps further confirm this. The model identifies distinct spatial signatures for emotional states, consistently highlighting frontotemporal and occipitotemporal hubs, and reproducing the well-documented motivational direction model of frontal asymmetry for positive versus negative valence. These aren't arbitrary clusters. They're neurophysiologically plausible, task-adaptive groupings that validate the architecture's internal logic. RECTOR represents a fundamental shift in how we approach neural representation learning. By unifying adaptive functional partitioning, block-sparse hierarchical attention, and a multi-objective self-supervised framework, it moves us past rigid anatomical priors and naive masking shortcuts. It delivers state-of-the-art accuracy, exceptional robustness to missing data and hardware variability, computational efficiency, and deep interpretability that aligns with established neurophysiology. This is the kind of architectural innovation that bridges the gap between laboratory benchmarks and real-world clinical deployment. If you want to dive into the mathematical formulations, ablation studies, and dataset protocols, the full paper is linked in the description. Let me know in the comments how you think topology-aware self-supervision will shape the next generation of brain-computer interfaces and neurodiagnostic AI. Thanks for watching, and I'll see you in the next one.